Hello, this is the section 6.3 lesson. In this section we introduce confidence intervals for estimating a population mean. Now the basic idea behind this section is almost identical to that in section 4.5, except that instead of working with proportions we're going to be working with means. And so as we illustrated in the past couple of sections, a sample mean x bar is an estimate of a population mean mu. Now that number x bar is a single number, and so we call x bar a point estimate of mu. But like in the previous section, whenever we estimate something, we want to measure of the accuracy of the estimate. And so we're going to measure that with what we call a margin of error, which, like in the previous section, is the maximum distance between the actual value of mu and the estimate. And then using that margin of error, we're going to calculate a confidence interval, which is a range of possible values for mu, as opposed to just a one number estimate. Now in this section we're going to discuss two different types of confidence intervals, one that we call a z-interval and another that we call a t-interval. And the calculations of these are very similar, and they're done the same basic way as what we did in the previous section. We're going to start off by choosing a significance level alpha, or equivalently a confidence level 1 minus alpha. Then we're going to get a critical value. Then we're going to plug some things into formulas, and we're all done. The main difference between these two types of intervals, the z and the t interval, is where the critical value comes from. In a z interval, it comes from the critical value comes from the normal distribution. In a t interval, the critical value comes from a a student t distribution. And so we typically use the z-interval when either we know the population variance sigma squared or the sample size is large meaning greater than 30. We use the t-interval when sigma squared, the population variance, is unknown. Now, the more commonly used of these two types of intervals is the t-interval, and so in this short lesson we're only going to discuss the t-interval. Now, the t-interval is called a t-interval because the critical value comes from the student t distribution. So let's briefly review the student t distribution. Student t distribution has a density curve that looks very similar to the standard normal bell curve. And so in this picture, the dark black line is the standard normal bell curve. In the student t distribution, we have these different degrees of freedom denoted n. And the student t density curve looks a little bit different for different degrees of freedom. They all look very similar to bell curve, but there is a slight difference. So here's the student t density curve for n equals 1, for 2, and then for 5. And we can have any other degrees of freedom as well. Now, like with the normal distribution, in the student t distribution we define critical values. And the definition here is almost identical to that for a critical t value. So we start off with p as a number between 0 and 1/2, and let capital T have a student t distribution with n degrees of freedom. A critical t value is a number denoted t sub p of n, such that the probability that t is less than that critical value is 1 minus p. And so this figure over here illustrates this idea. So we have here is a student t density curve with n degrees of freedom. Here's our critical value. And so the area underneath the density curve to the left of the critical value is 1 minus p, or equivalently the area to the right is p. Now, values of the critical value are given in table C3 in the appendix. And here we've shown just the top few rows of this table. And so we see across the top we have different values of p, and these are commonly used values of p, not the only possible values of p. And then over here we have the number of degrees of freedom. In this table the degrees of freedom is denoted r instead of n. And so r starts here 1, 2, 3, 5, and keeps going, and then it continues on here in this middle column. R is 40, 45, 50, and so on and so forth. So finding a critical t value is just as easy as looking up the number on a table. And so now we won't get into the theory behind this, but let's define the t-interval. So let x bar be a mean and s squared be the sample variance of a sample of size n taken from a population with unknown variance sigma squared, mean and mean mu. Okay? So let's stop right there. So we go out, and our goal here is to estimate this population mean. And so we go out, we collect some data, we calculate a sample mean and a sample variance, and we have a sample size n. And so we're going to use that information to calculate this confidence interval estimate of mu. Okay? So then let t sub alpha divided by 2 be a critical student t-value with n minus 1 degrees of freedom. So like in section 6.5, that number alpha is called the significance level. And so we're going to start off by first choosing that number, and then we'll use that to find the critical value. And this critical value has n minus 1 degrees of freedom. And so then this interval x bar minus t times s divided by square root of n, and then the upper limit is the same except that we add instead of subtract. That interval is called a 100 times 1 minus alpha % confidence interval estimate for mu when sigma squared is unknown. Or in simpler terms, it's simply called a t-interval. Now, this number 100 times 1 minus alpha % is called the confidence level, just like we did in the previous section. Now, this quantity t times s divided by square root of n that appears on both ends of the confidence interval is called the margin of error and denoted capital E. So then in this notation, our confidence interval can be written in three different forms. This first form is the form that's given in the definition, x bar minus e up to x bar plus e. This second form is the same, just given in inequality notation. And the last form is simply x bar plus or minus e. In our calculations, we're going to use this form. I like this because I think it more explicitly says what the confidence interval means. Now, the requirements for doing this type of interval are, number 1, the sample is random. That's always a requirement. And then number 2, the population is normally distributed, or n is greater than 30. That's the same requirement as for the central limit theorem, and that's needed because the central limit theorem forms the theoretical foundation for this type of confidence interval. So let's do a simple example of calculating a t-interval estimate of a population mean. So a random sample of 15 1-pound packages of shredded cheddar cheese has a mean weight of 1.05 pounds and a standard deviation of 0.02 pounds. Calculate a 99% confidence interval estimate for the mean weight of all such packages. And so we're going to go through the same steps as what we did in section 4.5 to calculate this confidence interval. The first step is to define the population mean being estimated. And again, like the previous section, when we define the parameter, we don't simply restate the question or restate the problem. We define what it is we're trying to estimate. So in this case, we're trying to estimate the mean weight of all 1-pound packages of shredded cheddar cheese. And again, we stress the word all here because we're trying to estimate the mean weight of all packages, not just the 15 in our sample. And so the second step is define the critical value. And so to do that, we need to first figure out alpha, the significance level. Well, our confidence level was stated to be 99%. Alpha is 1 minus that number, so we get 0.01. And then we also need to know the degrees of freedom. Well, degrees of freedom is n minus 1. In our problem, we were told that n is 15. So our critical value, t sub alpha divided by 2 of 15 minus 1, this is our number of degrees of freedom. Alpha is 0.01, divide that by 2, we get 0.005, and then 14 degrees of freedom. And so we look up this value of p, 0.005, and then this value of r, the degrees of freedom, and we look that up in table C3, and we get our critical value 2.977. Then next we calculate our margin of error. Here's our formula. We plug stuff in, t times s divided by square root of n. We do that arithmetic, and we get this margin of error. Fourth step, calculate the confidence interval. Again, here's our formula: x bar minus e, x bar plus e, and so we plug in those numbers, do that arithmetic, and we get our confidence interval. We would interpret that confidence interval in the exact same way that we did in the previous section. We would interpret this by saying we are 99% confident that the true value of mu is somewhere between these two numbers. Now, the 99% confidence level means the same thing here as it did in section 4.5. It means that if we were to go out and collect a whole bunch of different samples and calculate a confidence interval for each one, then about 99% of those confidence intervals would contain the true value of mu.
Lastly, let's talk about how we can do these calculations on the calculator. So press the Stat button, go to the Test menu, and then scroll up or down to option 8, the T interval. And it's called a T interval because we're calculating a confidence interval, and our critical value is a t-score. So if you select that, you should get a window that looks like this. Now the first thing we have to select is how we want to input our information. And we have two options, either data or statistics. If we have raw data, then we can enter that data into a list and then enter the name of that list, and the calculator take care of everything else. But in this example, we don't have data. All we have are summary statistics. Specifically, all we have are the sample mean, standard deviation, and sample size. So we're going to choose that option, and then we'll enter the sample mean here, the standard deviation here, and our sample size here. Next, we have to enter the confidence level in decimal form. We're told to calculate a 99% confidence interval estimate, so C level is 0.99. So select Calculate and hit Enter, and you should get a window that looks like this. The first row just reminds us what type of interval we calculated, and the second row is our confidence interval. Here's our lower interval limit, and here's our upper limit, and we compare those to the answers that we did by hand, and we see that they're identical. The calculator also outputs the sample mean, standard deviation, and sample size as we entered it. And that's just so we can double check our work, make sure we entered everything correctly. Now this calculator does not give us explicitly the margin of error, but we can very easily calculate that margin of error by remembering that the width of the confidence interval is just twice the margin of error. So if we take our upper limit minus the lower limit and divide by 2, that's going to give us the margin of error. So that's all there is to calculating the confidence interval and margin of error on the calculator.